So we need to trace basically this argument that's been passed into us backwards in time. So let's do that. We now need to trace that into the other worker process. And we need to figure out which other worker process actually sent this to us. It could be one of multiple ones. When you run this, it will look up which inferior sent us the communication or data from this operation. Hey everyone, today we're going to talk about how you can use LiveRecorder and UDB to debug multiple processes at once, and specifically when you have multiple processes that communicate with each other using sockets. When you record multiple processes with either UDB or LiveRecorder, you end up with a separate recording file for each process that you record. So if one process communicates some bad data to a different process, you may need to jump from one recording to the other recording in order to be able to trace that data back to where it came from. To illustrate that, we have a program called Run Cache Distributed. This is a program that simply comes up with lots of random numbers and calculates the square root of them, but it does so in a distributed fashion. If we look at this file, we can see that it's simply a bash script which runs a bunch of other programs in parallel. We have a single coordinator process which comes up with random numbers and then sends them out to be distributed, and it sends them out to one of multiple worker processes that receive these numbers, calculate the square root in some fashion, and then return the result back to the coordinator for the coordinator to verify. We're going to record all these processes in parallel, and we do that using LiveRecorder's record on program option. You can use the record command to the undo binary to run LiveRecorder now, so I'm going to do that. And as I said, we need to use the record on program option in order to specify which of the processes in this process tree do we want to record. Now we're interested in recording the cache worker and the cache coordinator process, so a pattern like cache and wildcard should be good for that. We also need to pass the program or script itself. Now as this runs, we see some output from the coordinator process. On each line it tells us the IP and port number that it's using to communicate with that worker, and on the end of each line we see a few example values of the numbers that are being sent to the worker and the square root result which is being returned back. Now eventually we'll see that the coordinator throws an error message because it gets some invalid result. There we go. So the coordinator says that it's received an invalid result because the square root of 1 should be 1 instead of 256. Now that sounds reasonable to me, but we're going to have to load up the recording to figure out how did we get to this result. Because we've been recording all these in parallel, we should now have a bunch of recording files. We can see we've got one coordinator recording and a bunch of worker recordings. Now, because it's the coordinator that does the verification and throws the error, that's the place where we have to start our investigation. So we're going to load this up in UDB. You can also use the debug command to the undo binary, so I'll do that. And this will load up our coordinator process. Now, because we are concerned with looking at all of these recordings as a whole, we need to tell UDB that it should look at all of them at the same time. We do this with the correlate directory option to the uload command and give it the current directory. And that will go ahead and extract the communication information from each of those recordings so that it can use that to correlate between them, basically figure out where did the information from one go to the other. And after that's done, we'll see that UDB now is aware of multiple different recordings. We can see that it hasn't actually loaded all of the recordings, but it's aware of them and will bring them up if necessary. With the information that we've extracted from these recordings now, we can also ask UDB to tell us about how they're correlated. We can see here that the coordinator recording and process, which is identified as the inferior number 1, communicates with all of the other recordings or processes, and the other processes only communicate back to the coordinator process. And that's what we would expect from this kind of coordinator and worker type topology. So now we're ready to actually go and investigate that failure and trace the bad values. And to do that, first of all, we need to go to the end of the recording because that's where this verification would have happened. So we use the ugo_end command to jump to the end of time and use any backtrace command to get our bearings. We're in the abort routine from the standard library, so we need to unwind a few frames just to get back into our code. Reverse finish lets us unwind the execution 1 frame at a time. So we'll use that the necessary number of times until we're back in our cache distributed.c file. Now we should be able to look at some of the source code. So I'll enable the text user interface mode and we can start having a look at what we've been handed. So this is where we can see we've aborted and we can see some of the error message that was printed out just about a few lines above us. We can verify that indeed we were passed the number 1 and the square root result 256. And we can see that the coordinator has determined that the correct value should be 1 instead. So we need to trace basically this argument that's been passed into us backwards in time. So let's do that. First of all, we need to do reverse finish just to see where this argument came from. It looks like it came from square root remote, some other variable. And at this point, we can use the last command. This command expects an expression, such as square root remote, and will take us backwards in time until the last time that expression had a different value. So after executing this, we can see we've gone a few lines up to where square root remote is assigned from the contents of some array or structure called result. So from the comment here, we can see that this must be some kind of packet, which I assume was sent to us from one of the worker processes. We still need to trace this packet buffer backwards in time, so we use the last command again. Now on the contents, so we dereference the result structure. That takes us back into a routine called receive from, which is from the standard library. So we go up 1 frame just to see where we call this function from. And we can see here from the coordinator process, this must be the place where we have received this bad square root result into this buffer from some kind of socket. So we know this is the place where we received the data from a worker process. We now need to trace that into the other worker process. And we need to figure out which other worker process actually sent this to us. It could be one of multiple ones. Because UDB loaded up that communication information before, it can actually do that for us. And it does that with the ugo_sender command. When you run this, it will look up which inferior sent us the communication or data from this operation. It seems to be inferior number 11. And when you hit yes, it will load up that recording in the background and switch to the exact point in time where this data was sent. We can see we're in the send-to function call, and if we go up one frame, we can see this is exactly where the worker process called the send-to function to send some buffer. If we go up a few lines, we can see indeed this is the same packet that we saw in the coordinator. Now we could use the last command here on the contents of send buffer, but we could also see that quite easily send buffer here is being populated by various different variables, including our square root variable, which has the incorrect result we were looking for. So at this point, we're now in a different recording, and we can trace this further backwards in time. Info inferiors will confirm to us that we're now in a different recording as well. We apply the same technique as before. We use the last command on the square root variable to see where it came from. And then we follow the results backwards in time until we see where it came from. Now here we do a reverse step to get into this square root cache calculate function to see which return statement actually returned this value. And we can see here that we seem to be going through some kind of caching structure, and we've hit some entry in the cache, and we're returning some entry which has been calculated at a prior time. Let's just double check that this is the bad entry that we're looking for, number 1 at square root 256. And then we can use the last command again on this entry to go backwards in time to find out when it was populated. Now this shows the real power of the last command. In the previous instances where we used the last command, we could have just used reverse next to kind of follow the flow of the program one line at a time. But in this instance, we would have had no idea at what point in time did the cache actually get populated. So this is where the last command is really helpful. It tells us this is the exact time where this cache miss happened. So we can see here in this entry, we've got our bad values, and we can now look at the surrounding code to see how that was constructed. If we look at number adjacent, we see that that is a completely different value from the one that we see in the cache. And that should suggest to us that we got some kind of casting problem. Whenever you have a casting problem, you should be looking at the storage types of your structures. The ptype command tells you exactly the type of your structures. And we can see here that the cache is storing unsigned short types, which cannot hold the high number which number adjacent is holding. If we look at the type of number adjacent, we can see that's an integer. So that's why we have a problem here. We're casting this big value down into something we can't store. And then later on, we retrieve that entry value as if it's correct. So to conclude, we've used the ugosender command to jump from one recording to another, and then we use the last command to trace the values internally within each recording.